So far, we've talked about using the EM algorithm for maximum likelihood estimation, or at least trying to get as close as possible to a maximum likelihood estimate. But it turns out that with a minor modification, EM can also be used for map estimation, for getting map estimates. And in this video, I'd like to tell you about how to do that. Now, it's always preferable to use a map estimate when you can over an MLE estimate, over a maximum likelihood estimate at least, because the MLE is prone to overfitting, and the map helps to avoid that bad behavior of the MLE. Now, so as usual, for a map estimate, we have to assume a prior. So let's do that. We will assume a prior p theta on the parameter theta. And our goal, as usual, in map estimation, is to find a maximizer of the posterior probability of theta given the data. And here I'm using, for consistency with previous videos in this section, I'm using just x to denote the data. It's the sequence of observations x1 through xn, but not any latent variables. So there are latent variables which are not sort of showing up in this expression. Latent variable z. So this is the goal in map estimation, and we're going to see how to use EM to at least try to approximate or try to get a map estimate. EM for map estimation. Algorithm is very similar to the algorithm for MLE. We initialize to theta 0. We initialize theta 0 to be some parameter in the space of all parameters. And then for t equals 1, 2, 3, and so on until convergence, we do the following two steps. First, we have the E step, just like, well, very analogous to before. It's going to be slightly different, though. In the E step, we have this function. Now we're going to have a function r. Before we had a function q. And it will be r of theta, let's see, I want theta t with theta t minus 1 is the conditional expectation, so this is going to look very similar, theta t minus 1 of log, the first part will be similar at least, of p of theta t. Actually, let's just make this one theta, not theta t. So r theta with theta t minus 1 log p theta. And this time it's the joint of x with z. Z is the latent variables. Given, well, I guess I should put it this way. I could put that, but since we're talking about putting a distribution on theta, we should say given theta. Given that x equals the observed value, little x. So we have this is the conditional expectation of this joint probability given theta. So it's sort of a conditional probability in some sense. Plus, so this is the different part. This is the new part. Plus the log of the prior for theta. That's this first argument. That's the E step. And this is the part that's different over here. So this is the new part right here. This is all essentially the same. And the M step, when we're doing map, is we maximize this thing. So we take theta t plus 1 to be a maximizer, a little space here, over theta of our theta with theta t. Oh, I guess that should be t, since we have t minus 1. T minus 1. Right. So when t is 1, we are getting theta t, and this will be theta 0. And this is just the same. So the E step, so you could either, put this in the M step or the E step. computing these expected values turns out to be the same. It's the same procedure that you use for ML, for maximum likelihood estimation, because this is just the same quantity. This is the Q. This is the Q that we had before. This is Q of theta and theta t minus 1. So the only part which is different is this log. And you could view this as sort of just modifying the maximization step. When you maximize, you also try to maximize. You have the sum, and so it's a balance between the prior and this Q. So that's EM for maximum a posteriori estimation. Very simple modification. And it turns out that you often have, doing the maximization can be done analytically when you have an exponential family and all that good stuff. All right, so I want to also show you that we can get the same guarantee for this procedure that we had for the MLE. In the MLE, we had that the sequence of likelihoods was non-decreasing, and we have the same guarantee for this procedure. Let's see why that's the case. Well, let's define this function capital L of theta to be the log of the probability of x with theta. So before, when we were doing MLE, we had this function little l, which was the log. So before we had this function little l of theta, which was the probability, it was the log of the probability of the data under theta. And now we're going to have this capital L, which will be the log of the probability of the joint. And considering the joint makes sense, because maximizing this conditional probability of theta, the posterior, is the same as maximizing the joint of x with theta, because this is the probability of x and theta divided by the probability of x, and probability of x doesn't depend on theta. So maximizing these two quantities is the same, and actually, of course, we can put the log in here as well. So that's why it makes sense to sort of think about the joint here. So let's look at this quantity. And if we can prove it for this, if we can prove that this is non-decreasing in the sequence of estimates theta 1, theta 2, and so on, then we will have that the posterior probability is also non-decreasing in the sequence of estimates. So this is what we want to show is non-decreasing here, this L, this capital L thing. So let's take a closer look at this. Well, we can factor this as log p of x given theta, the natural thing to do here, plus the probability, plus the log of the prior. And this first part is this is just this little l of theta that we mentioned before, just writing this p theta of x in a different way, right? Because p theta, this thing here, this p sub theta of x, is just another way of writing p of x given theta. It's just that here, when we put given theta, we're emphasizing the randomness of theta, but this means the same thing. So this is L of theta, the little l of theta that we had from before. So that's good. That's a good sign. We can use those sort of same results. And the results that we found if you refer to the video on the guarantee that we proved for the maximum likelihood case, we decompose this little l as q of theta with theta 0 for any theta 0, plus the relative entropy of the conditional distribution on z given x, the relative entropy of that. So this was, maybe I should put theta, which one comes first? Theta, theta 0 with P, the conditional distribution, with theta, plus the entropy of the conditional distribution on Z for theta 0. And now we also, so this was what little l was. This was what the result that we proved in that earlier video. And now we also have this extra log P theta hanging out. And now let's call this here g of theta 0. And let's call, well, I guess we don't need to call that anything. So remember that r of theta with theta t minus 1 or theta 0, we defined to be this thing. And so we can start matching up pieces here. This part was q of theta with theta 0. So that's here. And this is the log of the prior. So we get that this is equal to r of theta with theta 0, where r was defined above here, plus this thing, plus g of theta 0, plus the relative entropy. And the relative entropy is always non-negative, so this is greater or equal to this. Greater or equal. And with equality, when theta equals theta 0. Because when the two distributions are the same, then the relative entropy is always 0. So we get a very similar looking condition as before, and maybe just to remind you, before we had that little l of theta was greater or equal to q of theta with theta 0 plus g of theta 0 with equality if theta equals theta 0. And this condition was exactly what we needed in order to show the property that the sequence, so that implied that the sequence of estimates, I'll just put theta t less or equal to theta t plus 1 for all t, that implied this condition. That was the key thing that we needed. And then we got the nice intuitive picture with the, you know, the curves. And this is just the same. The only difference is here we have r instead of q, and we have this big L instead of this little l. So this shows us, so with using the same argument as in the other video, except with r instead of q, we have that this capital L satisfies the same property, non-decreasing in t. So we get the same guarantee as before. However, this doesn't guarantee that we're going to get a global maximizer. This alone actually doesn't even guarantee that we're going to even hit a local max. But it's at least nice to have this property that it's non-decreasing. That this is non-decreasing, so this is non-decreasing, and therefore the posterior probability is also non-decreasing as theta, as we get our sequence of thetas. So that's EM, the EM algorithm for maximum a posteriori. It's a very, very nice, very simple modification of the MLE case. And I hope you enjoyed that. Okay. Okay, see you later.